Okay, so our main source of energy for weather, and for that matter, for the oceans, is the energy that comes in from the sun. With Earth's orbit, we've got the tilt putting either the north or the south towards the sun at different times of year. We just passed the official start of spring a few days back, so now here we're in the northern hemisphere, we're tilted somewhat towards the sun. It's warming up. We're moving on into spring here. But now we'll look a little bit more closely at how energy behaves in the atmosphere and how this determines our temperatures. So we've got sunshine, comes in through space, reaches the atmosphere, and what happens? Well, for weather, we're primarily interested in the troposphere, our bottom layer of the atmosphere. And again, the troposphere is warmest at the bottom, characteristically. Yeah, it's got variation after all, it's dynamic. But characteristically, it's warmest at the bottom because it gets its warmth from the sunlight warming the ground. So we want sunshine for warming things up to come all the way through the air and reach the ground. Not all of it does, though. Some of it does get absorbed somewhere up in the atmosphere. Light hits a gas molecule somewhere up there, or maybe a bit of a cloud, something like that, and the energy is absorbed by that, warms it up, but that means it doesn't get down here and warm us up. Or the light coming in could bounce off of something, either kind of reflection, or it could encounter particles and be scattered out in all directions. Sunlight was headed down towards the ground. If it bounces off some other direction, it's not coming down to us. Scattering, well, kind of goes in all directions. Some of it keeps going more or less in this direction, but some of it not. So the reflection and scattering, both of these are tending to send some of that light back into space, not getting down to us. But some of it does go through. Now we look outside, we can see some light. There is some light getting through the air. Going through it, that's referred to as transmission. Clear sunny day, there would be a lot of it. Maybe 80% of the sunshine that hits the top of the atmosphere gets all the way down to the bottom. But of course, other days, like today happens to be here, it's cloudy, maybe just hazy, and a lot less light is making it all the way down to the ground. So we have our possibilities. We could have light energy coming in, and it's absorbed by some molecule up in the air, warms it up, but not us down here. Or it could bounce off, be reflected, could scatter out in various directions, again from interaction with the particle, or our transmission. This is familiar from other things, such as a window. Here we can see sunlight's being reflected, so we see a bit of the pattern of the sky reflected off of there. There's some transmission. We can see what's behind this window. And also, although it's a little tricky to judge just from this picture, it's a familiar observation that windows do absorb some light. It's not quite as bright behind a window as it is outside. Of course, other things in the air can have an effect. Pollution, like the picture here. Pretty obviously not getting as much light as we would without that pollution. There are natural things too. A volcano erupting could lead to less light being transmitted. A really big one, in fact, can cool things off globally because of the light being blocked. Okay, so we've got some light, it's been transmitted, reaches the ground surface. What happens there? Well, again, some of it will be absorbed, warming up the ground, so it reflects back off. And our measure of how much is reflected is the albedo. Alb Latin for white, like the albumin is the white of an egg. Albino is white. Let me help you remember what it means. So albedo is the proportion of visible light that's being reflected by an object. And here we have a number of different examples of Earth's surfaces. And no surprise, things that are more white, that's a high albedo. Things that are more black will have a low albedo. This is important not just for things on Earth. It affects, say, in astronomy. You're peering out with a telescope and barely see something. Okay, how big is it? Well, if it's white, you could get a lot more light reflecting off it, and you'll be able to see it even if it's smaller. If it's nearly black, then you're barely seeing it because there's not much light reflecting off it. It would be much bigger. So you have to figure out the albedo to figure out what you're looking at in a situation like that. But for here on Earth, we have a wide variety of different possible surfaces. For example, no surprise, a black pavement surface, or dark gravel, has a very low albedo. Dark green trees, very low albedo. White, dry sand, pretty high albedo there. Snow and ice, those have quite high albedos. And of course, we've got different things that could change the Earth's surface. If we had things warming up, there was more melting, and we got less ice and snow, and the albedo would tend to go down. Or say we cut down a forest and turn it into a shopping mall. Well, what color is the roof of the mall? We're changing the albedo, doing different things there. Reflection, you should note, there are different styles of reflection. We're most familiar with specular reflection, something like a mirror, where the light's reflecting basically straight back, and you get an image of things because of the direct reflection of that light. That's not something we see too commonly out in nature, but of course, light is reflecting off of all sorts of things. We can see them. We couldn't see them if there were no light reflecting off. So this light is reflecting, but it's somewhat scattered as it reflects. And this is referred to as diffuse reflection. For example, snow, highly refractive, got a very high albedo, but you don't look at snow and see your reflection. The light is scattered enough, you don't get a kind of direct picture of things, but there's definitely light coming off of the snow. Scattering. Again, this happens when the light waves encounter a particle. They can be sent off in all directions, but without the energy being absorbed. So all the energy's there, but it's now spread out instead of going the roughly straight line that we had coming in. Two types are important for light in the air. One is Rayleigh scattering, named after the fellow who worked out the math of it. Rayleigh scattering happens when the things doing the scattering are very small, noticeably smaller than the wavelength of the light. So this would be on molecule size for visible light. Rayleigh scattering sends the light out in all directions equally as a result of the scattering. It also makes a difference what wavelength of light. Shorter wavelengths, like blue, is scattered more. Longer wavelengths, red, those get scattered less. And so Rayleigh scattering specifically is why the sky looks blue. As sunlight comes in, it's got all sorts of colors in there, but the blue gets scattered more, and so we see that out in all directions. The red is scattered less, and so we see the sky looking blue, not reddish or not just plain white. But there are times when the sky is not blue. At sunset or sunrise, things tend to look more red. Well, the sunlight, the sun's very low angle, so that light has to come through quite a lot of air. It's going very much diagonally through the air instead of straight down. And going through so much more air, the blue has all been scattered away, and we're starting to scatter out the red. And so we get the red look of a sunset or sunrise due to Rayleigh scattering as well, which would also tie in for the color of Raleigh.